Hello, everybody. Today's session we continue by discussing about Blackbody radiation and the Blackbody radiation laws. Now we are going to focus on the two laws of Blackbody, where we are going to see what is a Blackbody, what are the Blackbody radiations. So even what laws of Blackbody we can use to clearly define a Blackbody. Here we have two laws of Blackbody. We are going to insist, we are going to look together. After also we shall see some questions answered related to these Blackbody radiation laws. Let's go ahead. So firstly, there is the two laws of Blackbody, Wien's displacement law and the Stefan Boltzmann law. And these laws are used to explain, to show the relationship between the body's temperature, even the intensity they can emit. So let's go ahead by Wien's law. Wien's law, it is a law that shows the relationship between the temperature, even the wavelength. So the higher the temperature, the lower the wavelength. When a body is able to emit high intensity, the temperature at high intensity has also lowest possible wavelength. Here there is a diagram we can use to show clearly define this one. It is a Blackbody curve, radiation curve. It's a curve that can show us clearly how these are related one to another. This curve is related to Blackbody. Okay, as we see, this diagram shows the body which is emitting at different temperatures. Here this is at 3500 Kelvin up to 5500 Kelvins. It means that let's take for instance this green curve. It means that this body at 5500 kelvins, at this maximum peak, the body, because at y you have the intensity, even at the x-axis you have wavelength. It means that at highest peak or maximum peak, the body will have highest intensity. It means that the highest intensity corresponds to the lowest wavelength. So as the law says, the wavelength at the maximum peak times the temperature the body has equals to the constant value. So, in brief, the first law, which is Wien's law of Blackbody, states that as the temperature increases, also the wavelength at the maximum peak decreases. They are inversely proportional one to another. There is another law which is Stefan Boltzmann law. Stefan Boltzmann law. Stefan Boltzmann law. It is a law also that explains about Blackbody radiation, where the second law says that our body, without considering how hot or cold, every body will emit the intensity, which is directly proportional to the fourth power of its temperature. So this is what we call Stefan Boltzmann law. This is the formula we use. The power of a body is equal to Stefan Boltzmann constant times the fourth power of its temperature. What does it mean? This is a perfect Blackbody. Here the emissivity will be equals to 1, and the reason why in the formula we are not getting what we call emissivity, because these are perfect Blackbody. We are saying if there is no if they are not perfect Blackbody, we will use the emissivity, because the power will be equals to the emissivity times the Stefan Boltzmann constant times the temperature, fourth power of temperature. So these are the two laws of Blackbody. The second law, which is Stefan Boltzmann law, states that The total energy radiated per unit area of black body is proportional to the fourth power of its temperature. This means that the temperature of black body increases, the energy it radiates increases very quickly. Even this curve can explain. If the temperature increases, also the intensity of the body will increase, because as temperature increases, the intensity also will increase. These are the two laws of black body, whereas Wien's law shows the relationship between the temperature and the wavelength at maximum peak, and Stefan Boltzmann law shows that every body, according to the temperature it has, it will emit radiation which are directly proportional to the fourth power of its temperature. No matter how hot or cold, everybody will be able to emit radiations. So let's look at the conclusion. We can conclude that these two laws help students understand how temperature affects the radiation emitted by a black body, where Wien's law tells us the wavelength at which a black body radiates most energy. It will emit most energy at its minimum wavelength. Stefan Boltzmann law tells us how much total energy is radiated depending on the temperature of a body it has. So the two laws are important. This concept will help us to explain why hotter objects glow brighter and different colors, as well as hot stars and other astronomical objects. Also, this curve will show at different colors, because the wavelength will determine the color of the body. So let's try to look on solve the questions related to this black body radiation. Starting for Wien's law, a black body has a temperature of 5000 Kelvin. At what wavelength does it emit most of its radiation? Let's look. We are going to apply the concept from the first law, which is Wien's law. Here we have the wavelength, which is unknown, and the temperature is known. Just we can apply the formula where we can use so that we can solve for the wavelength at maximum peak. So another question or another example related to Wien's law. A star's maximum emission wavelength is observed at 290 nanometers. What is the surface temperature of the star? Similar with the first one, here we can use Wien's law so that we will find the temperature at the wavelength which is the maximum. So let's look on Stefan Boltzmann laws. Calculate the power radiated per square meter by a black body at temperature of 6000 kelvins. The similar question with the first one, but here we can apply the formula, because these are the perfect black body. It seems that we consider the emissivity to be 1. So if we apply the formula, the power will be equal to the Stefan Boltzmann law times Z, the fourth power of the temperature, which is equal to 6000 K. Then we will solve for the power of this black body, this star. So this is the value we can get. So it's just to use the formula. And remember that the power equals to, or the intensity equals to the power of area, or power which is equal to the intensity times Z, area of the body. Now let's end by looking for this question related to Stefan Boltzmann law. The surface area of star is 4.5 times 10 power 18 meters square, and its surface temperature is 5000 kelvins. How much power does the star radiate? It's the same strategy. This is the area of the body. This is the surface temperature of star. So we can apply the same strategy where the power should be equals to the Stefan Boltzmann constant times area times the fourth power of temperature, so that you can immediately get the value of power. So the power will be equals to 1.6 times 10 to the power 27. So briefly, these are the key. Let's meet next time by looking about more related to this Stefan Boltzmann law. We will be able to know how to apply even the application of these laws. See you next. Welcome at this channel. Thank you so much.